hurry. Bernoulli's theorem. It's a very important theorem in fluid mechanics. Now, we studied the type of flow and all those things and the characteristics of flow and all those things. Now, what are things that we discussed till now in fluid dynamics? We are taking all those things into this particular theorem. The theorem states that the total energy associated with an ideal fluid in streamline flow remain constant throughout the flow. Now, to derive a mathematical condition for this Bernoulli's theorem, we consider a ideal fluid. I am taking an ideal liquid of density rho, flowing through a pipe, and the flow is a streamline flow, and I am taking a section of that pipe with the x and y as the cross sections, and at cross section x, the area of cross section is A1, velocity of entering is V1, and P1 is the pressure at this particular phase. And at this end cross section, area is A2, velocity of flowing out is V2, and pressure at this particular point is found to be P2. And you can see from the figure, the section of the pipe is raised from the horizontal ground, and cross section X at this place is effectively at a height h1 from the ground, and this is at an effective height of h2 from the ground. Now, when I say the liquid is flowing from lower to a higher level, here I will be supporting the flow that it has to flow from here up to that. Rising up means the energy is increasing. So from here I have to supply an external push from this point. That means that at this cross section X, there is a pressure P1, and at cross section Y there is P2. So P1 is found to be greater than P2. So if P1 is found to be greater than P2, as the liquid flows from X to Y, there will be a decreasing pressure, and therefore there is a decrease in pressure energy for the system. So decreasing pressure energy in pressure energy is equal to m P1 by rho minus m P2 by rho, where m is the mass in consideration, mass of the liquid, and rho is the density of the liquid. So let me take this as equation 1. Next, as we see the velocity of flow, here the large cross section is coming, and here it is the small cross section is coming. Therefore, we can find that the velocity V1 is less than V2 based on the continuity equation. According to continuity equation, we got area of cross section into velocity is a constant. That is, A into B is a constant. Therefore, area of cross section increases, velocity has to decrease. So based on that, we can conclude V1 is less than V2. That means as the liquid flows from here up to this across x and y, there will be an increase in kinetic energy is coming. So, increase in kinetic energy for the flow, that is equal to half m V2 square minus half m V1 square you can have, and that is equation number 2. Now you can see that the mass is actually flowing from a low level to a high level. Therefore, if that m mass is at this point, there will be a potential energy for that mass, and as it reaches over here, it is experiencing a greater potential energy. So, as the mass moves from x to y, there is an increase in potential energy is coming. And therefore, we can write increase in potential energy. That is equal to mgh2 minus mgh1, because h2 is greater than h1. h2 is greater than h1. So that increasing potential energy, let me equation 3. So for the system, we got the energy is pressure energy. It is decreasing as it flows from x to y, but there is an increase in what? Kinetic energy and potential energy. So knowing all these energies associated with this particular system, according to conservation of energy, total energy to remain constant. So for this isolated system, total energy to remain constant, that means that pressure energy plus kinetic energy plus potential energy must remain constant. So from the equations 1, 2 and 3, we can see that decrease in pressure energy is equal to increase in kinetic energy plus potential energy. Let us say potential energy. Okay. Then applying the equations for this conservation condition, we get P m into P1 by rho minus m into P2 by rho. That is equal to, this decreases given to the increase, half m V2 square minus half m V1 square plus mgh2 minus mgh1. Okay. Now, as we see, this suffix 1 and 2 I separated on either side by gap. M P1 by rho plus half m V1 square plus mgh1. will be equal to mp2 by rho plus half mv2 square plus mgh2. This is the statement I can get. So if I analyze this statement, you can see that this part is the total energy at cross section x, and this part is the total energy at cross section y. So total energy at x is equal to total energy at y. That means that the total energy for this ideal liquid remain constant throughout the flow. That means we can effectively take the condition here, that is m p by rho plus half mv square plus mgh remain a constant. This is what we can arrive at, and this is nothing but the statement of what you call Bernoulli's theorem. Okay, so we derived that based on conservation of energy.